Here we go, scholars. Let's stop using the long version of finding the derivative, and let's talk about the shortcuts. So the derivative of a function we know is its slope. So the derivative of a constant function looks like a horizontal line when you graph it. The derivative of a constant must be 0. So if f of x equals 5, f prime of x equals 0. We want to work up toward what we call the power rule. So think about raising x to an exponent. So x raised to a power. We figured out already the derivative of x squared. We could use that limit expression. The derivative is 2x. We could keep going. What if we wanted to take the derivative of x cubed? Well, we'd have to multiply out x plus h cubed. Pascal's triangle is here to help you remember where that comes from. And we get 3x squared. If I want to take the derivative of x to the fourth, it takes more multiplications out, but it all comes down to 4x cubed, and we can start to see a pattern. So 2x, 3x squared, 5x to the fourth, 6x to the fifth. This leads us to what we call the power rule. The derivative with respect to x of x raised to an exponent is the old exponent moved down to front to multiply times x raised to a new exponent, which is exactly 1 less than the old exponent. So here's an example. If f of x equals x to the fifth, f prime of x is 5x to the fourth. That 5 was the old exponent. It comes to the front to multiply, and my new exponent is 1 less. Turns out that this rule works even if my exponent is a negative number, even if my exponent is a fraction, even if my exponent is some kind of weird irrational number. So here's another example. If g of x is 1 over x to the fourth, as long as you can think of that as x raised to a power, we can use the power rule. So 1 over x to the fourth is the same as x to the negative fourth. So my first step is to rewrite g as a power of x. Now I can use the power rule. The old exponent was negative 4, so negative 4 comes to the front to multiply. And I'm going to raise x to a new exponent, which is 1 less than the old exponent. So negative 4 take away 1 makes negative 5. I end up with negative 4 times x to the negative fifth. Same goes here if I have h of x is the cube root of x squared. As long as you remember how to write a radical expression using a fraction exponent, this is a piece of cake to take the derivative. So I'm taking the cube root of x getting raised to the second power. That's the same as x to the 2/3 power. Now I can use the power rule. H prime of x is 2/3, the old exponent, times x raised to the negative 1/3. Negative 1/3 is 1 less than the old exponent. 2/3 take away 1 makes the negative 1/3. Alright, it was called the constant multiple rule. If there's some number multiplying my function, and I want to take the derivative of the function, I can factor that number out to the front and hang on to it, take the derivative of the rest of the function, and then multiply it back at the end. So if I have y equals 5 times x to the 7th, and I want to take the derivative, dy dx is that 5 that was already there multiplying, times whatever the derivative of x to the 7th is. Well, the derivative of x to the 7th is 7 times x to the 6th. So I have 5 times 7 x to the 6th makes 35 x to the 6th. Here, if g of x is 4 over 5x cubed, I can use this constant multiple rule and the power rule as long as I first rewrite my x as a power. So the 4/5 can factor out to the front, and then that would be 4/5 times 1 over x cubed. But 1 over x cubed is x to the negative 3. So think of this as 4/5 times x to the negative 3. Now I can take the derivative. The 4/5 waits for a second. I have the old exponent negative 3 comes out to the front to multiply. The new exponent is 1 less, so 1 less than negative 3 makes negative 4. I can multiply the 4/5 and the negative 3 to make negative 12/5 x to the negative 4. That's just the same as negative 12 over 5x to the 4th.